Octet Rule states that most elements are most stable when they have 8 valence electrons around them, like neon or argon, noble gases, to have noble gas configurations. But there are some exceptions to the Octet Rule. 8 is a good number, oct 8, but hydrogen is stable to have 2 valence electrons around it, helium 2, lithium 2. Now beryllium is stable to have 4, boron 6, nitrogen most often has 8, but if there are an odd number of electrons in an element, it can have 7. And then elements in period 3 or greater, they can have 8, but they can also have 10, 12, or 14. Usually whatever number will minimize formal charge the most. So considering these things, and considering that we need to minimize formal charge, let's go ahead and draw out the Lewis dot structures for sulfur dioxide and then sulfate. All right, so first, sulfur dioxide makes a happy structure. All right, so we want to make a skeletal structure in which we have the least electronegative element in the center, and then we need to add enough electrons onto each atom so that they have octets or filled valence shells. All right, so this is our happy structure. How many electrons are needed for this? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But how many electrons will be available? Well, sulfur, there's one sulfur, it brings 6 valence electrons, so 6 valence electrons come from the sulfurs. There are 2 oxygens, each one brings 6 valence electrons because oxygen is in group 6A, so there's 12 valence electrons coming from all the oxygens. There are 6 plus 12, 18 valence electrons to start with. Yet, our current structure has 20 electrons in our happy structure. So we need to remove 20 minus 18, 2 electrons from this structure. So go ahead and remove or erase 2 electrons. So we removed electrons, but now we need to move electrons so that all elements get filled octets. And so go ahead and say move these 2 electrons in to form a double bond. Now we can see that all of our elements have, all of our atoms have filled valence shells. 2, 4, 6, 8 electrons around this oxygen, 2, 4, 6, 8 electrons around this sulfur, 2, 4, 6, 8 electrons around this oxygen. But in step number 4, we need to minimize formal charge. So what are the formal charges on this structure? All right, so consider the number of electrons that come from the oxygen versus how many now belong to it. Now, oxygen brings 6 valence electrons. It's in group 6A. Yet, how many electrons are around it right now? 2, 4, 5, 6. There's a formal charge of 0 on this oxygen. What about this sulfur? Sulfur is in group 6A. It brings 6 valence electrons. Yet, right now, belonging to it, there are 1, 2, 3, 4, 5 electrons. 6 minus 5 plus 1. There's a plus 1 formal charge on this sulfur. And what about this oxygen? Oxygen is in group 6A. It brings 6 valence electrons. Right now, though, there are 2, 4, 6, 7. 7 valence electrons. There is a -1 formal charge on this oxygen. All right, so we have all this formal charge, but we would like to minimize formal charge. So we need to learn how to transfer the electrons. All right, so let me just redraw this so we can see it all again without all the clutter. Here's our sulfur dioxide as it is currently. And right now there's a +1 and a -1 formal charge. We want to get rid of some formal charge. Oxygen has a negative formal charge. There are too many electrons, negatively charged electrons on it. And sulfur has a positive formal charge. There are not enough negatively charged electrons on it. So we need to move some electrons from the negatively charged element to the positively charged element. Transfer these electrons in to form a bond between the sulfur and oxygen, so that now we get a double bond there. Now, what are the formal charges? All right, so now this oxygen, let's see, it brought 6 to the table, and right now it has 2, 4, 5, 6, 0 formal charge. This sulfur brought 6 to the table. Right now it has 1, 2, 3, 4, 5, 6. It has 0 formal charge. So does this oxygen. We've gotten rid of all of the formal charge by transferring those electrons in to form a bond towards the sulfur. And that's often a good way to get rid of formal charge. Move electrons in to form a bond. But wait a minute. Haven't we broken one of the rules here? Do we have a filled valence shell around the sulfur? Is there a full octet? Well, no, actually, it no longer has a full octet. Though the oxygens do, 2, 4, 6, 8 electrons around the oxygens. The sulfur has 2, 4, 6, 8, 10 electrons around it. Is that okay to have 10 electrons around the sulfur? Yes, because sulfur is in period 3. And period 3 or greater can have 8, 10, 12, sometimes even 14 valence electrons around them. It's okay. Everyone has a filled valence shell or is in another stable form. We've minimized formal charge, and we have the proper number of electrons. This is the structure for sulfur dioxide. And we'll see later that because this is the structure, sulfur dioxide has a bent structure, which will be important later. All right, let's try another one. Let's try sulfate. All right, so SO4 2 minus. All right, so sulfur will be in the center because it is the least electronegative element. Now make our happy structure, put enough electrons on everyone to give them full octets. All right, so how many electrons are in this structure? 2, 4, 6, 8, 8 more here, 8 more here, 8 more here. So there are a total of 32 electrons needed for this happy structure. 8 times 4. Now, how many will be available? Sulfur brings 6, and there's 4 oxygens. They each bring 6. So we get a total of 6 plus 24. You might say 30, but wait. There's a 2 minus charge. There are 2 more electrons than protons in this entire ion. Having a 2 minus charge means there's actually 2 extra negatively charged electrons. So add 2 more electrons to the number available. It's actually 32. So how many do we need to remove here? 0. All right. So we've also got full octets in everyone. Everyone's happy. You might say we're doing good, except we have not yet minimized formal charge. So now we need to account for formal charge. The oxygens here, they're all the same. They all brought 6 valence electrons, yet they have right now 2, 4, 6, 7 electrons belonging to them. So they each have a -1 formal charge. And the sulfur, it brought 6 valence electrons. Right now, though, it has 1, 2, 3, 4 electrons belonging to it. So it has a +2 formal charge. Too much formal charge here. Let's get rid of some formal charge. Remember, you can get rid of formal charge by forming bonds. Transfer electrons from the negatively charged atoms to the positively charged atoms to form bonds. This one transfer would give us 0 formal charge on the oxygen, but a +1 formal charge on the sulfur. What about if we transfer 2 pairs of electrons to form bonds? Now we get the following structure. Now, each of these oxygens still does have a -1 formal charge. And these oxygens here, top and bottom, though, they have 0 formal charge. They each brought 6 valence electrons to the table, yet they have 2, 4, 5, 6 electrons belonging to them, 0 formal charge. So no formal charge on the oxygens and the sulfur here. It brought 6, and it has 1, 2, 3, 4, 5, 6 electrons belonging to it. It also has 0 formal charge. So though there is formal charge, we have these 2 negative charges. We can't get rid of any more formal charge because to move the electrons in towards the sulfur would create positive charge on the sulfur. And it's preferable to have, and also additional negative charge on the oxygen. And we know that there has to be overall formal charge here. We know this because the formal charges of all of the atoms must add up to the overall charge of the entire ion. If there's a 2 minus overall charge for the ion, there must be a 2 minus overall charge somewhere. So we have to have the formal charge, and it's most stable to be on the oxygens. This is our Lewis dot structure here. Thanks for watching, guys.